All right, so we're going to do another limiting reactant example. All right, so in this problem, we have titanium oxide is going to react with two carbons, producing titanium solid metal as well as two carbon monoxide molecules. Right, and the problem says titanium metal can be obtained by this reaction, and when we have 28.6 kilograms of carbon, that's going to react with 88.2 kilograms of titanium oxide, we're going to produce 42.8 kilograms of titanium, right? And the question says, find the limiting reactant, the theoretical yield, and the percent yield, as well as the kilograms of excess reactant or reagent. Okay, so remember some of our guidelines, our steps for solving the limiting reactant problems are that first we need to figure out what the limiting reactant is. And so in order to do that, we're going to convert each reactant to grams of the desired product. And in this case, we're going to probably have it in kilograms because all of the other measurements are in kilograms, and even the excess reactants telling us in kilograms. So we're going to convert each mass of reactant to the mass of the desired product, and in this case the desired product is the titanium because it's telling us that titanium metal can be produced by this reaction. So that's the product that we care about. Okay, so just in general, remember we have our stoichiometric mole ratio conversion that we want to think, oh, we need to use that, right? Because we have grams of these reactants and we got to go to grams of a product. So one thing to something completely different, we have to go through the unit of moles. Okay, so here's kind of our outline here that we want to be thinking about in our head. We're going to convert each reactant, so kilograms of carbon, okay, which is going to be 28.6 kilograms of carbon there, and we need to convert it to kilograms of titanium. And then we need to also convert the other reactant, kilograms of titanium oxide, which is this 88.2, to kilograms of titanium, the desired product, right? And then remember, whichever one of these calculations is the smallest amount of the titanium product, that's the theoretical yield, that's all that we can make. And then the reagent or the reactant that gave us that smaller mass of product is called the limiting reactant. All right, so take a few minutes, pause the video, and do your calculations, and then we'll check that. So let's check our limiting reactant calculation. All right, so remember we're going to convert each reactant to desired product. So I'm starting out here with 28.6 kilograms of carbon. Since it's in kilograms, I'm going to go to grams because I need to use the molecular weight, which is in grams per mole, okay? So we'll just do our prefix, 1,000 grams of carbon per 1 kilogram of carbon. I'm still in mass, and I need to get to moles, right? So I'm going to use the molecular weight of carbon, and then now I'm in moles of carbon, and I can use the mole ratio from the equation. So I'm going from 2 moles of carbon to 1 mole of titanium. So now my moles of carbon will cancel. I'm in moles of titanium at this step here. And I want to get to mass of titanium, right? So I'm going to use the molar mass of titanium, okay, which is 47.87 grams. My moles cancel. I'm now in grams of titanium, and you could leave it like that, but it's just a really large number. So we can convert it back to kilograms, and essentially, you know, multiplied by 3 there, or by 1,000 there, and now I'm dividing by 1,000, so that kind of cancels each other out. And what I end up with is 57.0 kilograms of titanium. I rounded that up to 3 sig figs. Okay, so I'm going to do the exact same calculation for the other reactant. We're going to convert all reactants to desired product to see which substance is going to give us the least amount that's going to be limiting and run out. All right, so same calculation for titanium, 88.2 kilograms titanium. I'm going to go to kilograms to grams and then use the mass of titanium oxide to get to moles. Use my mole ratio. So 1 mole of titanium oxide to 1 mole of titanium. There's my 1 to 1. In moles of titanium here, I'm going to use the mass of titanium just like I did in the previous calculation. And then again, back to kilograms because it's a large number. And I end up with 52.9 kilograms of titanium. All right, so I'm comparing between these two numbers here, and this mass is smaller from the titanium oxide. So this is all that I can make theoretically. That's the theoretical yield, 52.9 kilograms of titanium. Theoretically, all I can make if I have a perfect reaction and have 100% efficiency, which that will never happen, right? And the substance or the reactant that gave me that number is this reactant here, titanium oxide, right? So this is the limiting reactant. Okay, so all other calculations would go through titanium oxide. So we have found the limiting reactant. We've also calculated the theoretical yield in that determination. And so next we're going to figure out the percent yield, and then finally kilograms of excess reactant. So we'll do those two calculations next. Okay, so now we're trying to figure out the percent yield and the mass of excess reagent or reactant. All right, so remember that our percent yield equation is equal to the actual yield, what we actually got whenever we made the product experimentally, divided by the theoretical yield, which is what we calculated from our limiting reactant. Theoretically, we could make that amount, which is the maximum amount you could possibly make, times 100%, right? And you're never going to ever achieve the theoretical yield. You're always going to have some error, so you're always going to have less than 100%. Okay, so the actual yield is given in the problem here. It says 42.8 kilograms of titanium is produced. So that's where that number comes from. So that's actually how much was made, right? Which goes here in the numerator. And then 52.9 kilograms of titanium, that was our theoretical yield that we calculated from the limiting reactant portion that we just found out, okay? And so we divide those two, and that gives us 80.9%, which is actually a really good yield. All right, so in order to figure out, so that one's done. In order to figure out the excess reagent, remember all other calculations, anything that might ever be asked in a problem, you always want to start with whatever your limiting reactant value is of your starting conditions, because that's going to dictate how much product you make. It's going to dictate how much other reactant reacts with it, and then how much is left over of any other reagents. Okay, so we want to use the limiting reactant to convert to grams of other reactant in this problem. Okay, when we do that, that mass of the other reactant, that's going to tell us the amount that was used of the other reactant, or the amount of the other reactant that was reacted. So if I convert this to this, the amount that I calculate of the other reactant from the limiting reactant tells me how much of this was used or reacted with it. Okay, so that doesn't tell me how much is in excess. It only tells me how much was used. Okay, so if I can calculate how much of this was used from the limiting reactant of this, so mass of this, use stoichiometric mole ratio to get to moles of this to mass of this, okay? That's how much is used. This is how much I had to begin with, right? So how do I figure out the amount of carbon in excess? Well, it's going to be the initial amount of carbon, which this is what I initially had when I added it to react with that, right? Minus the amount of the carbon that actually reacted. So that difference is going to tell me how much I have left over, right? Okay, so when we convert this limiting reactant to this excess reactant, this mass that I calculate, again, is the amount that was used or reacted. So then I have to take that and subtract it from the initial amount, and that'll tell me how much is left over. Okay, so again, we're going to do another stoichiometry conversion just from one thing to the other. So grams of one thing to moles of that, mole ratio to the other thing, and then back to grams using the mass of the other thing. All right, so my titanium oxide, this is my initial amount. I'm starting with my limiting reactant information that I have. So this is kilograms of titanium. That was the limiting reactant. I'm going to go to moles of the titanium, okay, using the molar mass here, so I'm at moles of titanium. I'm going to use the mole ratio to go from titanium to carbon, so that's a 1 mole to 2 mole, okay? So 1 mole cancels out here to 2 moles of carbon on top there. Now I'm at moles of the other thing, which is our other reactant that we're going to. And then I need to go back to mass, so I use the mass of carbon and get back to kilograms. So I should end up with 26.5 kilograms of carbon that was reacted or used. So to get the excess, right, I need to subtract it from the original amount of carbon, right, that was used in the reaction, and I get left over 2.10 kilograms of carbon. Okay, so we have another limiting reactant problem, and this will complete all of our examples for chapter 7. All right, so this is the reaction equation here. We have P4 plus 6 Cl2 goes to 4 PCl3. And the reaction mixture contains 45.69 grams of P4 and 131.3 grams of Cl2. Okay, after the reaction is fully complete, okay, what mass of the excess reactant remains? Okay, so it's just telling us what is the excess reactant amount. Okay, so in order to figure that out, we kind of have to go through all of the steps. We have to first figure out the limiting reactant. We don't necessarily need to figure out percent yield or anything, and we actually can't because we don't know how much of this product was made, but we do need to figure out the limiting reactant. And then once we know the limiting reactant, then we can use that to convert to the other reactant, all right, to get the mass of that one, and that's going to tell us the amount that was used, and then we can subtract that used amount from the original amount that was given up here for the reaction, and that'll tell us how much is in excess. Okay, so the first thing we want to recognize is that we have to calculate limiting reactant even though it doesn't say. All right, so that's our first step. So we're going to convert each reactant to the mass of the desired product, right? Okay, so I have the mass of P4 and the mass of Cl2. So we're going to go mass of each reactant to moles of those reactants, and then I'm going to use the mole ratio to go from the moles of the reactant to the moles of the desired product. In this case, there's only one. And then once I've used my mole ratio to get to moles of desired product, then I want to go back to the mass of the desired product using the molecular weight of them. Okay? So in each of these calculations here, you can pause the video to take a look at the work more clearly after you work it through yourself. Okay, but each one you'll see we go from the mass to the moles of each reactant, and then I'm going to use the mole ratio, okay, to go from P4 to PCl3 here, going to the moles of product, and then using the mass of the product to get me mass that I can get with the P4 reactant. And then the same thing, I got mass of Cl2, I want to go to moles of Cl2 reactant, and I want to go to the desired product, so I need my mole ratio between 6 moles of this and 4 moles of this. Here's my stoichiometric mole ratio. And I forgot to cross out my units here along the way. Okay. And then back to my mass of desired product, PCl3, and I get 169.6 here. Okay, so then we compare between the two masses, right? And the smaller mass is all that we're going to be able to make. So that's my theoretical yield. The problem doesn't tell me or ask what the theoretical yield is, but that Cl reactant gave me that smaller mass of that product, and so Cl2 is, right, the limiting reactant there. Okay? All right, so I figured out that the limiting reactant is Cl2, and I need to figure out the excess of P4, because P4 is an excess. So Cl2, how much is left of that? 0. Limiting is completely used up. All right, so I want to know how much of the P4 is left over. So remember, the next step is all calculations go through or start with the limiting reactant information, and that is the starting amount of Cl2 that I have. So I'm going to start with 131.3 grams of Cl2, which is given in the problem up there, and I want to convert the mass of the limiting reactant to the mass of the other reactant. And in this case, the other reactant is P4, okay? So I'm just using my stoichiometric roadmap to do that. And so we got mass of CO2 limiting to moles of the limiting, and then I want to go to moles of the other thing, which is P4. So I'm using the mole ratio, 6:1 there, okay? My Cl moles cancel, and then I want to go back to mass of P4. So I use the mass of P4, 124 grams per mole, and I get 38.3, right? So remember, this is the mass of the other reactant that was used or reacted. Okay, so that's the amount that's used. That's not the amount in excess. So then we have to take the initial amount that was used in the experiment, right, which is the 45.69 grams, and I need to subtract it from the amount that was used when it reacted with the limiting. And I end up with an excess amount of 7.30 grams of P4 there.